Yeah, I do have a trouble talking about the embedded segment, and often not classed as the sexy place to be when people have got the mobile phones and everyone's showing off their iPads and things. So we do our best to try and make it as interesting as possible. What we're going to do today is touch on, really it is a move to semiconductors, obviously being used much more widely, but then, a few technical tips on what people are doing to try and make more energy efficient designs within the silicon process. Finally, touching on areas of wider use of semiconductors, and hopefully one or two, if you like, small wins we can have in helping save this planet a little bit and save energy a little bit. So the vision of ARM, and we've come from a background of particularly mobile processing, baseband processing, and we're taking that further now to be the energy efficient processor where we can connect all things together in a very energy efficient way. And performance is always very important, but actually getting that mix of performance, power, cost is really, really essential in an engineering environment. So, we're trying to make life easier for people while actually keep maintaining the amount of energy. Obviously what's driving all this need for, semiconductors at the moment? Everything is beginning to be connected. We're certainly talking a lot about the Internet of Things, and we're seeing this right from the mobile phone, which is an obvious choice of a connected device, to potentially the smart metering systems. Electric charging vehicle stations are a great example of machine-to-machine connectivity, where whether it's measuring data or whether it's passing payment, there is a need for everything to be connected so it can react much quickly. Obviously, at the same time, we've got to be concerned about the energy, and we've got to design everything in a very energy-efficient manner while meeting the performance requirements. One thing we all hoped, actually, was cloud storage and processing was going to be a great easer of energy in terms of, well, we won't need this great big brick in our hand that's got huge sort of performance requirements. We can offload everything. All that's effectively doing, though, is driving much more data center usage, much more higher-end processing, and actually that is going to be a big area of concern and something we need to address in the near future. And ways of looking at how can we make, while we've still got a very good performance device in our hand, how can we reduce the power consumption in the data centers? So where we are today, we've seen, and I keep regularly updating this slide far too often now, 25 billion devices shipped over the last 20 years. Started originally with the Acorn Computing, but where we're seeing this go now, obviously 25 billion largely was mobile consumer handsets, but where we're seeing it go now is to 100 plus billion and a lot of sort of sensor type systems. We think within the smart grid, people are going to regularly monitoring data, monitoring the energy usage so they can get a better balance. So it could be in sensors, it could be in smart meters, it could be on an industrial site or, pretty much in the home. But we're seeing a very, very wide range of uses now for energy efficient processing. And also in the plugged-in devices. It's always a case in the plugged-in device, reducing the energy tends to reduce the cost of the device as well. The plastics around the silicon become cheaper. So there's massive benefits in actually reducing the energy in the silicon and helping the cost, drive down the cost, and therefore driving the scale of the product. So we have to think about power. And, every time you do a design, it's really got to be at the forefront of everything we do. And the problem is you can't do one thing in a semiconductor environment to have a complete success. It really is a number of small things that effectively somebody could easily go and ruin for you by doing something a bit daft at the end of it. But you've got to think, certainly from the beginning of the design, we start with the architecture. So use the ARM architecture, the x86 architecture. You've got to be thinking when you implement that, it's effectively doing an operation based on the software instruction. How small can I make that? How much sort of like transistor gates do I use to do that operation? You've got to think, what's the best power efficient way of doing that? And that's something ARM did, particularly, Apple chose ARM 20 years ago in the Apple Newton as the low power architecture. So we've regularly been focusing on that. We're going to be running off a battery. We're going to really reduce the heat. What do we need to do to continually enhance the architecture while hitting the performance requirements but saving power? And then you go into this other area, which there is no right or wrong answer. It really depends on your application. The implementation techniques. So what you're seeing a lot in the market at the moment, especially on our mobile phone handsets, it's quite common. Do you have a single core doing one thing, or do you have two cores where you can distribute the load across multiple cores? Now, I think this comes down to what your application is. If anybody's designing something that's got a specific function, and when it's on, it's running one thing all the time at full speed, you probably could get away with a single core, and it'd probably be ideal. Because when you're running it, it's on full speed, it needs to be a particular performance, you know what it is. And then when it's finished the job, you turn it off. In the mobile handset world, it's a bit harder, because people use their handsets in very, very different sort of use cases. Having the multiprocessing idea might work a little bit better, because maybe I'm only doing my email, I could potentially just have one core on, the other one's turned off. That's a great way of saving power. But as I say, you have to start analysing what are the use cases of the actual final product and what silicon or what semiconductor package is suited better. And then you move on to the manufacturing technology. So, some engineers have gone ahead, designed a core architecture, implemented a chip effectively, but they've got to go and get it manufactured. This has a massive issue relating to cost, relating to performance, relating to power. I took an example here. We have these what we call ultra-low leakage. This is TSMC is probably the most famous semiconductor manufacturing organisation, and they have a specific process designed at, if you like, low-cost microcontrollers running at very, very low power. These systems tend to have what's called a flash memory system in them, allows the end customer to develop software. It's a great way of trying to drive down that power depending on the manufacturing technology. In the other sort of higher-end mobile processing world, you would be on a more advanced process. It would be much more expensive, but because it does allow more performance, you could potentially clock things back and save power that way. So, do I kind of overspec my manufacturing technology, but then run it a little bit slower, run it with a lower voltage? I can actually still achieve a lot of the work I need to do, but save some performance and power. And then finally, on top, you've gone ahead, you've done your hardware, you've made your chip. It's great. I can advertise this great milliwatts per megahertz number, but it fundamentally comes down to the end product, the software design. And it's really hard to read, but this is just an example of where we've taken, it's effectively a SKIA, which is a bytecode interpreter from Google's engine, and we optimized it for the ARM instruction set. So this is software optimization. This is something a lot of people can do with their end product. And you find that if you tweak things long enough and hard enough, and I do agree it takes quite a while to do this, you can get some performance benefits. If you get performance benefits, again, that relates to power consumption. If you can do that with a lower voltage, with a slower clock speed, you tend to find you get quite a good power saving. So if people are continually thinking about power as they go through the design process, as I say, lots of these are small wins. It's 3 to 5% in the architecture per every time you do one of these iterations. But ultimately, it can make quite a big saving in the end. So it's a continual process of ever developing, ever doing better. And these are different people from different organisations have got to be thinking how they're going to do this implementation. And then obviously once we've got our silicon out there, hopefully we've got some great smart meter designs out there that are running really optimized software. We've got mobile phones out there that are running optimized software. Where's all this data stored? So we're seeing everybody moving now to a data storage farm, some data center. Google, I think, were an example recently that didn't they just invest in a wind farm or something to power one of their data centers? I mean, it is an issue, and lots of heat come out of those as well. So we need to look at what we can do to reduce the power within the infrastructure. So as more and more people are having handheld devices, we've got to start looking at what's going on behind it, what's happening in the back office, and sort of find ways of reducing the power consumption within the infrastructure. So we took a look at this, and okay, it's not an ideal prediction, but it gives you an idea. Servers back in 2002, you look at the growth rate of where we are now, and if we just populated our 2020 server centres with those older processing systems, are we saving 350 million tonnes of CO2? Gives us an idea of if we just carried on as usual and didn't continually reinvent things, we're going to have a real big energy issue. And this is just on the data centre side itself. So a couple of things that are starting to happen in the market regards data centers. Virtualization. Again, this is similar to the multi-core argument as well, whether it's done in hardware on its own or hardware and software, a mix of accelerators within a system. But what you're doing there is distributing your workload across a number of processing elements in a software environment. Cooling the system, I mean, just in fact the way you place your racks has a massive issue on the power consumption within a data center. So finding ways of using smart cooling systems to drive down the temperature of the processor, which will reduce the power consumption as well. Storage, we see a great move to solid state. We can, as we move to solid state storage, we can save more and more power. So we can save power in the actual control units of the hard disk drives. We can move to solid state, and again, ways of actually reducing power there. And then finally, on the CPU side, it's maybe selecting the right CPU for the job. So if we look at sort of web-based servers, we might not need the full high-end processing that the particular Intels are doing today. So what we look at is, a mix of, say, ARM-based, sort of more consumer-devised processors that could actually do a good enough job in a server center for a particular application. And again, it's finding the right CPU for whatever the maximum processing limitation is required. So we think if we move to a sort of multiple ARM processor system, again, we can see quite a significant saving in the power consumption. And I've got two slides of just some examples of poor design. I do find this quite interesting, and a lot of this refers back to a bit of the software implementation. It's not optimizing your software for better performance, but it is how do I work my software so that it can do some intelligent things around the hardware. And okay, it's an old one, but you take the old desktop PC that showed you the power consumption in watts of when it was on and actually doing some work, and when it was on but wasn't doing anything. So, I mean, surely the sensible thing to do there is to sort of find somewhere about, is it displaying new images? Is someone writing to the frame buffer? And could we do something to sort of turn that screen off? And, when we start adding the standby mode, I often wonder whether they go low enough there. I mean, do we need a granular level of standby modes? A lot of it is related to wake-up time. So the standby mode is set, and it goes, okay, I'll put standby mode, and when someone presses this, it'll wake up in a second. But you probably could have a number of standby modes that says, over a period of time, if no one's looked at this for a day, well, I'm quite happy for them to press a button, and it wakes up in 3 to 5 seconds. If you do these different levels of standby, it all involves switching off voltages to various different semiconductor components within the system. But actually, it's a way of saving more and more energy. And then, this was just an example of the gaming systems. I mean, so this was, it was a study in the US that basically was saying that they think they could save around 7 million tons of CO2 just by the way people use their gaming machines. Most people were leaving their gaming machines on, and they were on for over 5 hours a day. So actually, the blue one there showing you who's actually playing a game and then actually turning it off. And it's very, very few people. Most people are playing the game and leaving it on, or playing the game for a long period of time. So what we need to be doing there is, again, looking at ways of monitoring the time, monitoring the response, and finding a way of turning off that silicon used. And games are a really good example because they're very high processing. And when they're on, they're usually on full power. Normally all the gaming engines within the silicon are all turned on. So actually, when they're off, you can save a significant amount of energy because you can just stop, turn off all the clocks, turn off the voltages to a lot of the areas of the silicon. So again, some intelligent software required from the OEM's perspective to just say, well, what are the trade-offs? How can I allow my final customer to wait a few more seconds for something to turn on? And it's just a matter of what you're used to. But there are ways of driving down this and saving energy in quite a significant effect. So I mean, to conclude, there is no doubt that the use of electronics is increasing globally. We all want an easier life. We all want to be able to do things quicker and easier. But at the same time, while the growth of electronics is continuing, we need to find a way of doing it in an energy-efficient manner. It usually means selecting the right, semiconductor for the job, the right processing point for the right performance level, and continually looking at new manufacturing technologies to make things, operate at the lowest possible voltage. So I think really, I'm hoping with the use of a lot of the sensors and a lot, we keep using this term smart in here, but the smart technology around the sensors, if we can drive manufacturing technology to be very, very low power, we will be able to see a benefit of implementing a smart grid with lots of very low power sensors around. We're going to collect lots and lots of data. I mean, maybe we can find ways of manipulating and using that data for much better effect. But while we're doing that, we don't want to be wasting a lot of energy on the semiconductor systems around the system that are actually collecting the data for us. So it's doing the best job we can with the tools that are available. And that's all I have for the moment. Thank you.